everybody. I hope everyone's having a wonderful day. So today we're going to be picking up from where we left off, talking about logarithms and oftentimes properties you can find in relation to big O. So today I'm going to be focusing in on how the base of a logarithm can affect asymptotic terms in terms of big O. So the first thing I want to start off with is talking about a well-known formula. We're going to prove this formula. It's called the change of base formula for logarithms. What it says, and keep in mind I didn't write down the domains for all the values. I'm just assuming what we've been doing previously. So I'm just assuming valid bases for the logarithms. And of course appropriate domains for x. And that's essentially it. So I'm going to consider when log base of a of x is equal to the following. What this formula actually tells you is that you can convert between two different bases. So if I have a base a, I can convert to base b, but I gain this term in the denominator of this fraction here. So I'm going to prove for you how you get the change of base formula. And we're going to use this in proving our next big O claim, which is going to basically boil down to saying that the base, as long as it's a valid base, if it's just some two fixed bases, it makes no difference. So if you like counting in base 10, or you like counting in base 2, or if you like counting in some weird real number, you can totally do that. Big O notation, there's not any concern of anything. You'll see what I mean. So let's prove the change of base formula. What's the first thing I usually do? I try to invoke some definition, and then we see what we could do from there. So I'm going to say invoking the definition of a logarithm if log base a of x is equal to y. What does that mean? Then a to the y, remember that's the base, that's the exponent, and this would be the result. A to the y is equal to what? It's equal to x. Now what I'm going to do is I'm going to take logarithms of a certain base to both sides. Remember, I can do this because doing such an operation is in fact a function, and since if they're equal to one another, they must also be equal when I apply the function. So I talked more about that last time. Well, in a previous talk, well, I talked about it before. The point is that we can do such a thing with this equation. Taking logarithms of base b to both sides of the equation. The equation a to the y is equal to x. You get what? You get log base b of a to the y is going to be equal to log base b of x. Right? Now we're going to apply the power rule. Like I said, this power rule is very useful. Next, by the power rule, of logarithms, log base b of a to the y is equal to what? I can pull this y out front, right? It's y times log base b of a. So what can I say then? So log base b of a to the y is equal to log base b of x if and only if the following is also true. Log y times log base b of a is equal to log base b of what? X. Now, what do you see that's interesting about y? Remember what y was at the beginning? I told you y is equal to log base a of x, right? So I'm going to use that. And y is equal to log base a of x, implying log base a of x times log base b of x, log base b of b, log base a of b, b of a, it should be b of a, log base b of a is equal to log base b of x. All I've done is I've substituted in what y was. Remember, y is equal to log base a of x. So now what am I going to do? I can just simply do the following. Therefore, by dividing both sides of the above equation, I'm talking about this guy, the above equation by log base b of a, we obtain so I'm just going to divide both sides of this by what? I'm dividing it by log base b of a. So I'm going to take log base b of a and divide on both sides. So that should eliminate this term. That becomes 1. And then I end up with something on this side, right? Log base a of x is equal to log base b of x over log base b of a. Which was what we sought to prove. And we're done. So that says which was what we sought to prove. It kind of melted in the microwave. So anyway, so that's the proof for the change of base formula. And I want to show you how you can use this change of base formula to prove an interesting but nuanced idea about big O in terms of logarithmic terms based on the base of the logarithm. Often, computer scientists work with the binary logarithm. I kind of melted in the microwave. The binary logarithm, that's just simply log base 2 of n. So the base is 2. However, some write log n like this without any mention of what the base is. Often in computer science circles, they mean the base is 2. However, in other communities, it might be that the base is in fact 10, because base 10 counting. Some people might consider this to be the natural logarithm, which is often written like this, ln n. Some also write the binary logarithm, by the way, by lb of n, but often in computer science circles, this will usually be log base 2 of n. Now, there's actually a nice feature of logarithms in asymptotic notation that I want to point out to you that's not necessarily relevant to this point, but more so to the fact that you can even get away with doing this and not really caring which one of these bases you've selected, whether it be base 10, the natural logarithm, or a binary logarithm. So I want to show you that. So I'm going to say summate log n to mean other bases. Example, log base 10 of n. I'm going to say this does not matter in big O. So very often what I'm going to be telling you is that if somebody just writes big O of log n, it won't really matter what the base is, even if you're familiar with the convention that usually computer scientists like to work in base 2. Though I usually encourage people to be more precise, so if you mean base 2, write base 2. But that's oftentimes something that tends to get glossed over. So what I'm going to do is I'm going to use as an application of the change of base formula, I'm going to prove the following claim for you, and you'll see why this would be very helpful. Assuming valid bases A and B, prove log base A of n is big O of log base B of n. So I give you two bases that are valid. I'm going to show you that you can jump from one to the other. So if this was, say, base 2, I can go to base 10. If this was the natural logarithm, I can go to base 2. If it's base 10, I can go back to base 2. That's the big point I want to really get home to you. So oftentimes when people write big O of log n, they might mean the binary logarithm, but the point is inside of asymptotic notation, it doesn't really matter. That's the big takeaway here. That's one of the big properties I want to point out to you. It's more of a, I want to be more precise kind of deal, which I recommend you do anyways. So what do I normally do? I say we find constants. So I need to find those two constants, right? We find constants, C. Remember, C is a positive real number, and n0, which is a positive integer. That positive integer symbol sort of just melted there. Such that for all n greater or equal to n0, log base A of n is less than or equal to C times log base B of n. Now this is where I'm going to use the change of base formula. So watch this carefully. Observe by the change of base formula that log base A of n is equal to log base B of n over log base B of A. So if I jump from one base to another base, I end up getting this multiplicative term of 1 over log base B of A. Does everybody see that? And remember, I'm allowed to use any positive real constant in the definition of big O. And this 1 over this would indeed be a positive real number, right? So I'm going to select that. I'm going to pick C is equal to 1 over log base B of A. Then notice that log base A of n is less than or equal to 1 over log base B of A times log base B of n, which of course is equal to log base B of n over log base B of A, which of course this is also equal to log base A of n for all n greater or equal to 1. So what should I pick for n0 then? I say it right here. Remember, when you always specify your domains for which you make your statements, finding n0 is very quick and very easy. So just remember that. You should generally write quantifiers for any statement you make. It's usually a good idea. Choose n0 is equal to 1. Therefore, by the definition of big O, log base A of n is big O of log base B of n. Bingo. So just the big takeaway here. So remember that if I give you any two valid bases, I can convert between them, and it only differs by some constant factor. In terms of big O, this just means that the base doesn't really matter, as long as it's just between two fixed bases. So if I have base 2 versus base 10, E, whatever you'd like it to be, as long as it's some fixed constant that I have for the bases. Well, constants. So that being said, I hopefully have shown you a couple of neat properties that we can use for logarithms that reflect properties that we can use and apply when we talk about big O.